There's two levels.
All right, welcome back, everybody. So every school, well-established school, has a tradition, and our school is no different. We do have a tradition. Every year, we have a lecture given by director of our school and actually director of Center of Frontiers in Nuclear Science, and now also associate laboratory director of BNL. Abhay Deshpande is going to give us introduction to scientific origins of the electron-ion collider.
Okay, all right. I'm very glad to come here from home. And normally I'm here these days only on Fridays. And so I was excited. I told Socorro this morning that I'm really excited to come here on a Wednesday and spend the whole day here. So, this is supposed to be, we give this lecture or some kind of this lecture in the first week so that students get a bigger picture overview of what the whole project is about. I especially like to talk about the scientific origins of the collider because there are lots of things that have happened over the last 30 years that have actually motivated a project like this. And I'll show you later in the talk as to how many projects were attempted around the world to address this kind of physics, and only one worked. And I think we understand, at least I have opinions as to why this seems to work. It's not worked yet, still more time to go, but at least we have an optimism that this is going to happen. But I would talk about it from the scientific and social point of view. The scientific origin is really important, what I want to emphasize later. So I will split this talk or this presentation into two parts. One is about where the project is, just an introduction of the project. What is Electron-Ion Collider? You heard about it in various talks so far, but as a peripheral mention. Now I'll tell you what the project is, and you can ask me, it's at a high level introduction, but you can ask me any questions, I will fill that up. And if needed, I'll upgrade the slides to include some of those things. So this year on February 6th, there were two milestones that we celebrated at Brookhaven National Lab. One was the end of operations of the relativistic heavy ion collider after 25 years of continuous and superb operation. It is very critical that we understand the value of that to what we are going to do in the next 25 years. Really important that Rick, the science and the accelerator ran as efficiently as it did over the last 25 years. I'm going to talk about that a little bit. It's a truly remarkable project and very, very high level of success, known in the complex of Department of Energy and internationally for its success. The reliability that was shown, the accelerator components that were developed, the new ideas that came through, all that was important. You heard Christoph Montag today on the accelerator side. I hope that he gave you an introduction to what it takes to get there. So I'll comment on that part first. Then I will go into the EIC. I'll tell you why it is now ready to go forward. And I will allude to the fact, and you will hear that throughout this school, as to that it is really at the frontier of nuclear and accelerator physics. So that's really important for you. One thing that this is a slide I used on 6th of February. It's really important to understand that there are a lot of people behind us. You know, when a scientific project really succeeds, there's a scientist come out and they present the results, and we all are happy to take the limelight. But there's a huge amount of activity that goes on behind the scene that keeps the accelerator going, that keeps the lights going at the lab, and that's really important to understand. And that was the context of this slide to get this going far beyond just the scientist part. And of course, funding agencies like DOE, Congress, etc. So we are always curious about fundamental structure of matter. And over the 300 years of investigation, scientific investigation, we have learned a great deal by looking deeply that the matter is made up of molecules. The molecules are made up of atoms. Atoms have nuclei in the center and the electrons around them. And it goes down to the nucleus. The nucleus we understood about 100 years ago were made up of protons and neutrons, positively and neutral particles. And then about 1960s, we learned that those protons and neutrons were not fundamental. Experimentally, we saw the evidence of quarks. And at that point, there were ideas about the fact that the quarks are bound together by something called the gluons. And the gluons bind the quarks together inside the proton. Unusually, differently than electromagnetism, they actually carry the color charge, and that's the critical part that distinguishes them from photons, and hence the QCD from QED. I think these are things that you all learned in undergraduate studies, but where we are going now, we are going to look in great detail of the interactions and the study of gluons inside the protons and nuclei. So the quest of understanding fundamental structure also happens to be journey back in time. And I think people who are into graduate school now would immediately make that connection, right? And the connection comes from here. We believe there's evidence of Big Bang in the beginning, and then there was an evolution of the universe as we see it today. At some point, there was only energy, and then small particles were formed, the slightest of them. The quarks might have been formed, the electrons, neutrinos, and then they coalesced together to form protons and neutrons at some point, and then higher level nuclei were formed. That evolution is something that we know has to happen starting from energy to small particles to small nuclei to where we are today. Colliders allow us to go back in time. Because go to high energies, the higher the energies, you're now exploring higher and higher, you're putting higher and higher energy into the particles that are visible to you. And a high density, high energy, you try to break them, and you try to create the situation that existed at the beginning of the universe, and that's what you try to study. Both Rick and the future EIC are sitting on the transition, but looking at different aspects of the early universe. And that's something that you have to see in the bigger picture. So Rick did that very effectively. For 25 years, it ran, and have you seen the Rick picture so far? Was it in the accelerator talk today? So you know that there is the source, which is a low energy source of polarized protons as well as nuclei, that then gets injected into this LINAC, and then gets accelerated into something called the booster, boosts the energy to about 200 MeV. Then it gets into the alternating gradient, this is about 2 GeV. This goes into the alternating gradient synchrotron, which gets to protons about 24 to 28 GeV. And then from 28 GeV, it goes into this transfer line, and then goes into this 2 rings, which used to be called RIC, the relativistic heavy ion collider. When I say beam, it really means bunches. A cloud of protons passes through. It's about 20 centimeters long and about a few microns in diameter. And that cloud comes through and gets into the relativistic heavy ion collider. And bunch by bunch, it goes to either the yellow ring or the blue ring, the yellow ring or the blue ring. They are going counterclockwise. And so when you fill the ring at 24 GeV, then you turn on the magnets to accelerate them. That can go up to 250 GeV, 10 times more in terms of protons. And then because we are using the same magnets, if I instead had a nuclear beam, nuclear bunch, it would go by the magnetic rigidity ratio. It's about 1.79 or 2.5. And that's why you're at the highest energy in the same magnet you can achieve is about 110 GeV. So now you know that you can do protons going 250 GeV in 2 rings counterclockwise, and they collide. They can be collided into these 2 experimental areas. There were 4 other places that we did not use in the recent times, but when we started the program, in addition to these 2, we also had Brahms and Phobos. These 2 experiments ran for about 6 years. Phoenix ran for about 16 years and then was taken over by something called Super Phoenix, and STAR ran for the entire 26 years of operation. And these are sort of the event shapes that are saying this is where it ran. If you went into the ring About 2 months ago, before the 6th of February, it looked like this. You could walk in here, you can see, you can drive a bicycle sitting there through the collider. It's about 3.8 kilometers in circumference, okay? All right, so here is what happened. When you build a collider, and you probably got that introduction today, you have a fixed strength of the magnet. So when you accelerate, if you want to change the energy of collision, you need to change the energy of the beam. That means you have to change now the strength of the magnet. And if you know a little bit of hardware, to go from the dynamic change that was required to go from 24 GeV in collisions in a stable way to 250 GeV beams, there is a large, we call large dynamic range that is needed. And that's seldom available to any collider in the world. But because we knew that we would need to understand the nuclear matter that we were going to create at different energies, this was inbuilt in the capability of the magnet. So the dynamic range of the magnets of RIC that take you from 250 GeV to 24 GeV if needed, that the injection energy, we call it, injection from the AGS itself, is something rather unique. When you go to higher energy, the particles get boosted. So if you have a beam that looks like this in transverse dimension, it's moving that way. When you boost it, they come closer, and they get boosted, they get closer together. And so naturally, the cross-section size decreases. So it's easier to get more collisions at higher energy than at low energy because you have a cloud, which is extremely rare when it is low energy and naturally becomes very sharp and short in transverse dimension, and you get additional thing. Then further than that, you can focus it. So at the highest energy, we had to play all these tricks. These are not easy to do. We could do this for multiple energies. Astonishingly, 49 different combinations of nuclei and energies were used. You can scan any collider in the world right now, ever being built or has been run. You will never see more than 3 to 5. This is really, really unique and a critical reason why we want to also use this to build the EIC, because that will need a large change in the energy that is available currently in the hadron side, at least, only with the RIC. That's why it's a very big plus point of this as to we are using this. So we had to take very different views and develop accelerated technologies. Eventually, we actually measured luminosities. This is the number of collisions per section, per cross-section area. It's a measure of how intensely, how well we can increase our study possibility by increasing the number of events. That was 40 times more than the design. Most colliders in the world are reaching reaching the design luminosity in about 10 years. And if they go up, it's a 10% increase, 50% increase at the most, because some new technique was used. This was 40 times more. This is also unheard of in terms of, so this is another thing why my personal respect for accelerator scientists has grown tremendously, because they come up with ideas working closely with experimenters like us, and we ask on demanding new things for them, and they learn, and they actually try to implement. So, and the last thing I want to emphasize, it's the only collider in the world in which the protons are polarized, meaning all the spins, or 70, 80% of the spins inside that bunch, that align with the magnet that you can put it in. This is very critical for the spin physics discussion that you will hear in this talk. So for the spin physics to understand the proton spin, this part is essential. So we did create gold-gold collisions. We had this quark-gluon plasma. What surprised us? So we knew we were looking for this quark-gluon plasma. And if you asked me what the properties of the plasma were, before RIG turned on, there was no conclusive evidence of quark-gluon plasma, that we had released quarks and gluons for that fraction of the time. But at the same time, people had written imagination, what would it look like? Well, there were lots of surprises, and surprises in physics are always good. If you write a theory, and then I do the experiment, and I agree with everything that you say in the before theory, then it's great. It's great for you, but we have not learned anything new because we knew what was going on. Maybe the details would evolve, but here there were very stark things. So at that time, we measured the temperature. It was the hottest matter ever created up to that point. Expected to be a gas. Behavior was expected to be a gas, and it flowed like liquid. It actually had flow properties. You could see in transverse dimensions how particles were flowing in the detector that looked like it was coming from a liquid flowing in that collision. They measured the viscosity of it. It was really, really small. It was like an ideal liquid, the most ideal liquid that people had seen, like better than even the liquid helium. Again, a strange thing. And the interesting thing to think about it is you started with a gas of hadrons, you collided it, you increase the temperature. Normally, when you have something, you increase the temperature, what happens? Liquid melts into gas, right? You have a gas that you melts into a liquid. That was strange. This was completely unusual and really something that was new, and we learned a lot because of that. Property of the medium was also very interesting. It was very, very dense, so the jets that came out of it were quenched. You could actually measure the energy that was deposited through this and then interpret that as the property of the machine. That was also unusual and very high. On the proton spin side, before going into this program in year 2000, we knew that the quarks alignment carry about 25% of the spin of the proton. That means 25% of the proton spin comes from the quarks and anti-quark together aligning or misaligning with them. And we were wondering why that should be the case, what role should gluon play? Well, over the last 20 years, we have measured that. And what we have found is that outside this quark, we measure about 30% of the contribution that comes from the gluons. And that begs the question as to where is the remaining spin? And that's something that you will hear about in these lectures about the orbital angular momentum of quarks and gluons. It's part of the GPD program that tells you, and the TMD program that tells you there exists transverse motion. If it is transversely motion, and with limits of the proton size, there has to be a connection to orbital motion. So those are the conceptual ideas that are there and connect the science of RIC to the EIC. And I want to finish this with the impact. There were about 300 trillion collisions over this time. 450 petabytes of data were recorded, 3,500 scientific collaborations, 650 publications, and about 650 PhDs. And we expect that this will continue in the next 10 years because we haven't finished the data analysis. So we've done 30 years to 25 years. There's going to be another 10 years of data analysis that will be required. These are some of the citations. But the most important thing, I believe, is that the science of quark-gluon plasma and proton spin now start appearing in textbooks. And I think that's really the hallmark of what impact we make. And the lower you go in that, the more important your science is. Think about it. Newton, you learn in high school, right? That was important. Then you learn our relativity sometime when you're making the transition. Now we are reaching the grad and undergraduate textbook, which is a good thing. But we are making that impact. Okay, so February 6th, the undersecretary came into Brookhaven and pushed this red big button, and that dumped the last fill of the RIC. It was an article that they published, the only US collider shuts down, for a new one may rise. And that was the beginning of the start of the EIC era, in our opinion, because the same day he declared a very critical decision, CD decision that's important in the life of many projects, that was declared also in the same day in the afternoon. He declared it at Brookhaven. These are some of the last celebratory pictures taken just after the fill was ended, and it was really a bittersweet occasion for most of us who have been involved with RIC for the last 25, 30 years, but also those who are aspiring, like us, to build the new electron-ion collider for almost the same time. Yeah. So what's going to happen? So with this, you know what that was? This was the injector going in. And if you see, there's a yellow and the blue ring. What we plan to do now is to take the blue ring out and inject or construct an electron beam facility in its place. So you see the yellow part remains, and there is a red ring there, which is the electron ring sitting in the same tunnel, no new construction, but the injector part of the electron is sitting here. So this is the source, this is the accelerator, and then injects, and there is further acceleration here. And eventually we'll have possibility of colliding the beam in two different experimental areas. Currently, there is money for this one here, which is called the EPIC Collider Detector, and you'll hear about it in the school. And then eventually, we hope that there is going to be another detector, the second detector, which will come at the different location. But the main aspect of it that we use about $2 billion of investment. So if you wanted to build such a collider on a greenfield today in the US, it would be $5 billion. And what we're claiming is that for $3 additional billion over the $2 billion investment over the last 25 years, we can achieve that. And that's really important for taxpayers and the DOE, et cetera, et cetera. So it's really important to keep that big picture in mind. I think you heard a lot of things yesterday. I believe there was a big discussion about AI. Is that correct? In the evening? So we'll have more. But you need to understand that AI is not going anywhere. And we have to use it for our purpose, for the appropriate purpose, not the inappropriate purpose. But also you have to train yourself to think is if AI can do this, then you want to go one step higher. I was just telling this to my son last night for some pattern recognition. It's really true. If your AI can do it, in 5 years, AI will do it. If AI is better at something, you better let it go. But then it doesn't mean that you're out of job. You actually can rise up. And so now, how can I use that AI? And we are doing that. So I think it is going to be the first large-scale facility in which the controls of the machine and optimization will be done by AI. When we turn on the accelerator, even after 20 years, we needed some specific experts in the control room who knew how to control the luminosity, the intensity, the polarization. And if they were not there, we would suffer, which means what? We would take longer to get to the highest luminosity, which meant, and running this collider, I can tell you, is about $1 million a week. So if I don't get to the best optimized tune of the machine that produces the physics, if I take 5 weeks to do that out of my 30 weeks of operation, then I'm not doing justice to the taxpayers who are paying for the research. But if AI comes in and I find the tune based on all the history that it knows, finds all the parameters and gets the best optimization done in 2 days, then that's a good thing. It's not just for the public, but it's for us too, because now we suddenly start getting a lot more data and best beams faster. And that's really being implemented very nicely now in the accelerator. Same thing with the detector. You saw the design. You will hear about this if you're not already. The design and the analysis, the pattern recognitions, everything in the analysis part will be done here. That is data analysis and simulation will be AI bent. And then I'm sure that theorists will also take that data and interpretation will have a lot more of AI involved. So I think this is going to be part of it. I heard the discussion. I added this slide not to challenge, invoke any, negative things, but I think we need to think about it seriously. So what are the difference between RIC and EIC? Why are we doing this? So think about RIC as smashing two watermelons like that. And then you look inside. Of course, you're creating a new form of matter because of the energy. But think about EIC as you're cutting the watermelon with a sharp knife. The electron is the sharp knife. It doesn't have structure, so it breaks. It doesn't break. What breaks is the watermelon. But because you have control and precision of the electroweak physics that you know very well, you can study the strong interactions very, very precisely. So use the precision of electroweak to study what we don't know. So think about it that way. It's sort of complementary. So the three things that, and I will come back to, is how we arrived at these things. Three highest level things that we decided were literally Nobel Prize worthy questions are: how do we get the mass? So you've learned that Higgs boson is the origin of mass. This is the base of everything. Yes, it is the origin of the fundamental particles' mass. All the quarks seem to get mass from there. I think we understand that process. It's an understood process. The leptons might get the, electrons, muons, tauons might get there. Neutrinos we are not sure all about, but anything massive neutrinos will get there. But if you just add the masses of the quarks inside the proton and know that the gluons are massless, you can explain about 1 to 4% of the mass of the proton, depending upon where you make the boundary of what is part of the quark and the gluons around it. Where do you make that cut? But somewhere around there, 2 to 2.5%. The rest of the mass has to come from the interactions. And the simplest way to talk to public about it is that there is energy there, because the quarks and gluons are not stationary. There is energy associated with it that relates to the motion, maybe transverse motion, orbital motion, that has to contribute to the total mass. And that's where the origin of that is. And there are ways you'll hear about in the school as to how to separate them and how to get to their mass. Those who are involved in the Jefferson Lab program, the solid experiments and I think Hall C also has a program where you look at JPSI production. And I think there are roots of the measurement that we will do at EIC are in that program, and EIC will do the same thing in the mass studies. And one of the people who sort of was critical in understanding how to relate that observable with the mass is Dima Karzev, who is sitting there and listening to me. The proton spin, right here, we want to understand not just the alignment very precisely of the quarks and gluons, but the orbital motion, the three-dimensional picture. That's why it's called the imaging of the proton. That part of the program is called imaging. You'll hear this word imaging. But the imaging is because we respect the three-dimensional aspect of the proton. That's how I interpret this. So far, we've been only looking at one dimension, which is the momentum dimension, and we only have one x and q squared, one x dimension. And now we are going to talk about transverse motion and transverse distribution that naturally goes into the interpretation of that. And last but not the least is the gluon-gluon interaction. I told you at the beginning that the distance between the interaction between gluons is possible because they themselves carry color, which is drastically different than the electromagnetism. And I like to think about it as a Gedanken experiment. You take an electron from infinity and you bring it to your lab and you make it stationary. What do you expect will happen? You observe as you're decelerating the electron coming into your lab, you radiate photons because you're giving up energy. When it comes to a standstill, it will have a fixed electric field around it and nothing else will happen. It was a fixed state. You think about a quark doing the same thing and you make it stop in your lab, if you're able to do that, then what happens? You'll radiate the gluons as you're coming through. But when it stops, it's there. The gluon interactions are still there. That interaction will emit other gluons of lower momentum, of course. Energy is conserved. The momentum can also always be smaller. The gluons will fit into 2 into 4, etc., etc. So there is a evolution around that quark. The explosion of number of gluons, even in a stationary state. I think this is something that you can think about, and it's alluded to in the Nobel lecture by Frank Wilczek, Origin of Mass in 2004. And you will see this description coming through. Now, it's a Gedanken experiment, of course. The important thing is to remember is that in this, the quark is free. There are no free quarks. But the idea is there, right? There's very different behavior. And that behavior is something that we want to understand. By going to a region experimentally where you enhance the number of gluons. And where do they come from? That's the highest energy, or the lowest x, we call it. X meaning momentum fraction. And that's what we are talking about here, to look at the small momentum fraction gluons that are naturally created in either in nuclei or at the highest energy proton. So this is something that we will want to study. And there are things that are between them, which I will not mention now. But this is the high level summary of the science. There are lots of things additionally we can do that happen. So this is what we are doing now. We're going from RIC, we're going to the electron-ion collider. I'll pause a minute now and tell you the history of it. Why did we come up with this idea? Why was it important to go in that direction? And I come back to finish to tell you where the project is. So here on the left to right, these are all the designs of the EIC that have gone through from 1999. What we used to call it the E-RIC was the electron and colliding with the RIC. The workshop at Yale, and then again one at Brookhaven. Then there was a LINAC ring design in which there was a LINAC, a 5 or 10 GeV LINAC, then a small ring here, and then collide at one interaction region. We call it the 12 o'clock region. Then it evolved into another place where there was a Jefferson Lab type ERL system here, 2 GeV, 4 GeV, 8 GeV, 10 GeV, and then would collide with one. Around 2016, we came up with a stable design here. We said we'll just inject through a LINAC and do this. And this is where we are now. Why am I telling you this? These are all things that were relevant at the time and allowed us to evolve with the science. Either the science was driving the design requirement, or if the accelerator physicists came to us and said, hey, we can do this new thing, and we can improve this beam or that quality, then the physicists would go back to workshops and say, how can we use that? So the interaction between the accelerator scientist, the experimentalist, and theorist was intense over the last 25 years. And you'll see that in all workshops that we see, there's always this, it's not isolated. They don't live together separately in their own worlds. They really interact. And that is reflected in the evolution of the machine as well as the physics. In 2002, the papers that we were written, and I'll talk a little bit more about this, there were no mentions of GPDs. Because GPDs didn't exist. We didn't know what they were. Theorists knew a few of them, but we didn't know that. We had just started learning about TMDs, the transverse momentum distributions. They were not taken seriously until Rick, in 2002 and 2004, measured for the first time transverse spin asymmetries, left-right asymmetries, which were huge, 40%. And theory guidance before that used to be, oh, these are soft physics effects. They should be less than 0.1%. When a theorist tells you that, a respected theorist tells you that, we take them seriously. But when you experimentally measure it, that's something that you get surprised by. And that's something that people realized that TMDs were serious. They were perturbative quantities, and the whole field led by Italians, our friend here, the host is also part of that early transition. The Anselmino group in Italy and et al., they just developed it at that point and made it very, very real. But if you look at these papers here around that time, TMDs were mentioned with no GPDs. But the science evolved, and we were now looking at higher intensity because the LINAC ring designs that is mentioned here, the LINAC gives you ability to go to very, very high luminosities, the number of particle collisions per second per square centimeter. Why does that help? Because LINAC, you have one beam coming through, hits the proton, gets up. In the ring design, the previous one, the same electron is hitting the proton, their bunch, as they go around for hours together. What happens if I increase, and you probably heard it from Christopher Montag this morning, if you increase the intensity in both beams, then you're concentrating the electromagnetic charge in a very small region, which means that one beam can destroy the other. Yes? In the ring design, that is expensive because that means I have to fill the ring again. In the LINAC ring, it's in the design. That means you don't worry about the electron bunch. You just make the whole as intense as you possible. If it gets destroyed, who cares? I can recover the energy, but that's by design. I can get a new bunch in. So the transition from inclusive measurements, you know about inclusive, right? Bernstein must have talked about that. You scatter only the electron. You don't worry about the hadron final state. But if you wanted to worry, you need higher luminosity. If you want it to be exclusive measurement, that means also look at the target fragmentation, you need even higher luminosity. But as soon as the accelerator physicist told us, hey, we are going to give you Linac ring that is going to reach you 10 to the 34 in luminosity, physicists became excited. So, oh, now we can do a lot more physics. So the physics evolved, yeah? And then, of course, the details of that evolved. Eventually, we are on that part. I think I'll skip that fast, but the main thing I want to emphasize in the inclusive part here, where only the scattered electron is measured, everything that we want to know about what happened in the partonic collision is based only on the scattered electron energy knowledge. Because the initial energy is known, the initial angle is known. If you measure the outgoing electron very well, limited only by the cost of building a calorimeter in your detector, yeah, you can do the best job you can. When you start looking at this, then you go to semi-inclusive and exclusive, and that's where you want to measure other things, and the cost of the rest of the detector comes along. Yeah. Another thing that came up in the previous talk at the end of Kong's presentation. A simple way of doing this is you have a fixed target geometry. So the target is sitting there, and the muon beam or the electron beam comes through and hits it, gets scattered, and it also pushes the target in that direction. So the target fragments are also going in the same direction. The higher the energy, the more forward the final states are. Yes? If that is the case, it's more difficult to separate the scattered muon and the separation of the target and the beam fragment. Which part comes from the quark that you hit, and which part that comes from the aligned momentum for the rest of the target. There is no way to separate that because they're always very together. It becomes a huge challenge for the detector to separate them, to see if there are correlations there. When it comes to collision geometry, the proton is coming from here, the electron is coming from here, the proton is coming from there, or the nucleus. At this point, the electron is flying up there. The target, the quark that was hit was typically going in the central part there, and then the target fragmentation keeps on going generally in the same direction as it was coming from. So now your measurement ability is much, much better. So that helps tremendously over the fixed target experiment, as he concluded his lecture about the deuteron measurement with the neutron. Yeah. So this is something that is very natural in collider geometry, but less appreciated, especially by people who have never done colliders. It's much easier to do that physics with exclusive physics in the collider than in the fixed target for this reason. Okay, all right. So there were 7 proposals in the late 90s for the electron-ion collisions of the future kind. This came from the physics that I will be talking about, and I'll show you some plots that were. But basically, they wanted to do the exclusive physics, the semi-inclusive and exclusive physics. So measuring the target and the beam fragment was important. And we didn't know, we were not efficient enough to do that. So people understood we had to go to a collider. So these were all the collider experiments. The DAISY, which I was involved in the first place, was a 300 GeV collider, the Hera collider. I think Bernd must have mentioned it. Yes, Bernd Soro, yeah. So 300 GeV collider. And all we wanted to do was to study spin and put nuclei in it, right? And then you have the EIC at a higher energy, or what we call EIC now. It was technically challenging, but it could be done. And I'll tell you why I think we didn't succeed. Then there was a proposal at GSI in Germany for a smaller energy collider. I'll show a little bit. GSI Grenoble was very similar. And then on the US side, in the same timeline, 90s, I will again mention a little bit more. There was one at MIT, the one at Brookhaven, this is ERIC that we are talking about now. There was one at Jefferson Lab, which came later, and then there was one in Indiana. The MIT and the Indiana proposals were based on their existing facility. They had in-house low energy proton or nucleus or electron beams, up to 1 to 2 GeV. So they said, oh, we want a collider. We can use this beam. So, and we were doing the same thing. I was suggesting the same thing, that we have the RIC. So let's put the electron beam on it. So everyone was thinking about upgrading their own facilities. Here too, very similar. So here's the list. So 300 GeV, polarized Hera, polarized protons, or electron nucleus. And here are some of the people that were involved at that time. The problem was that we were told we had only 3 years to do the physics. It was a cheaper program, 3 years to do the physics, but you could do only one of them. Either you do electron-proton with the polarized beam, or you do electron nucleus. And that meant that we split ourselves. We were fighting with each other. Because if you get only 3 years, then we were all competing, not fighting, competing for the proposal. Eventually, Hera management was not so keen. That didn't work out. And I'll talk a little bit about that later. There was the ENC, the European Nucleon Collider, 1997 proposal, about 30 GeV in center of mass. Now, fixed target experiments, as you know, are between 1 and 5 GeV. Sometimes you can reach data at 10 GeV, but about 5 GeV is the average. Even with the highest energy muon beam fixed target experiments, about 4 GeV, 5 GeV. That's all fixed target. Here was the first one that reached much higher. And then, as I said, Indiana University and MIT had proposals between 3 and 7 GeV. We had the 100 GeV proposal. The best thing we did in 2000 was all the US groups came together. And we said, the science is the same. Let's look at the best option and go there. And the 3 groups combined the effort to join the ERIC proposal because the hadron beam existed. The polarization was planned at that time, 2000. So RIC had not run then, it just started. And the nuclei were expected to be there. So we really focused ourselves on this and started developing this proposal. The strength in unity was really, really important. It didn't happen in Europe for various other reasons. And the 3-year time given at Hera was just too small. And we were split community. This is the slides that I thought I would just show you how simplistic the ideas were for the proposal. This is a talk that I gave, I believe, at Brookhaven in 2002, where we said, you know, it's interesting to go to low X because the history showed us that low X always gave us surprise. That's very fundamental. Low X means gluon interaction. I was not thinking, I mean, theorists knew, understood it at that time. I, as a postdoc, didn't know this. It's not that I didn't know, I just didn't appreciate it. Let's put it this way. That the gluon interaction, which happens now, which coincidentally we can talk about it low X, was not looked at it. It was experimental observational. That you go to low X and you get surprises. And those were the sort of structural surprises, high Q squared structural surprises that were mentioned there. The spin surprise that I was involved in to understand the proton spin, the quark spin puzzle that people talked about at that time, that the quarks do not carry all the spin proton of the proton, was a big surprise at that time. It was called the spin crisis in some scenarios. And then there was a rise in the F2 structure function, again, probably mentioned in Burn's talk at low X at Hera. That was a surprise. Nobody understood why that would increase. Now I understand it. Now we understand it. It is the gluon that makes it low. But those are all the next ones that were there. And then there were spin surprises. And here's a list of things where spin was really, really important, including the spin puzzle that I mentioned to you. And at that point, we had seen some aspects of transverse spin physics. But again, if you see, I have put in question mark because people were unwilling to believe those asymmetries. Where large asymmetries, people didn't understand TMDs. People had no concept of that. And that was the reason why those talks are like that. The reason why I felt that going to high Q squared and low X was necessary is because of the fixed target experiment I was working on at CERN. And here is the SMC, the spin muon collaboration data from 1996. It's the G1 spin structure function of the proton. And this is the best fit NLO QCD fit done by a group of Alterelli et al. And then naively, I said, I want to see what happens low. And that was the extrapolation given to me by the people. And that was very different than what we used to use at that point For the lack of data, we used to use this extrapolation to get to the total curve under the human spin structure function that is also talked about as first moment of the spin structure function. And if you've not heard it in lectures, you should in some lectures in this. So that's important because we actually were able or planning to measure the curve, the area under that curve, the first moment of the proton and the first moment of the neutron. And the difference between them is a very important spin rule called the Bjorken sum rule. And the Bjorken sum rule, the difference in the QCD part on the left-hand side can be exactly connected to parts of the electroweak physics. That's the beauty of it. The left-hand side, the more precise you can calculate it's great or measure. And the right-hand side is purely an electroweak thing, which is beautiful. It connects the standard model, parts of the standard model very, very nicely. And this was our reason for it. But we didn't know this. And so this created a lot of discussion in the field as to if really the extrapolation is going this way, we should be able to measure this because it's a large asymmetry going negative. And a similar plot was done for neutrons, and that also dives down like this. Now we understand the reason for it, the QCD behavior, the evolution behavior, but this was not very well known. This was the first time an NLO calculation was done at that time by the group by Baul, Forte, and Ridolfi. This was the consequence of it, that you looked at this low X, and suddenly you see a small difference in the Reggie part, which used to add, but now we subtracted from it by looking at this extrapolation, and the area under the curve now is the negative part. So you look at that, and then you subtract that, and that started creating issues of the spin rules, et cetera, et cetera. And then on the right-hand side, on the structure function F1 or F2, this is measured at Hera, and this is what we know today, or even as we know it in 1998. This line is kinematically the same as that. This is Q squared, and this is for different values of X, going all the way to 10 to the minus 5. This goes to 10 to the minus 3. You can see that there is no data here, no data here. The region where you see the scaling violation, the slope of these structure functions, which is the evidence of the gluon region, that's the part which is missing, and it's still missing. So why did I go into this detail and make this simple argument? The argument we made for the EIC was that 100 GeV center of mass or a 300 GeV proposal at Hera with polarized protons, we would be able to fill up this gap, look at the gluons with high precision using the electroweak probe. So if you look at the 7 proposals that you saw, I showed you on 4 on the US side and 3 on the Europe side. Only 1 survived. And you saw why. Because the closest one came to looking at this region was the ENC proposal at GSI, which was 30 GeV. The rest of them were 4 or 5 GeV. We would not have come out of this region. We would have been sitting again here. So the power of going to a new XQ squared region where QCD cannot be predicted is really important. And I think it saved us in this proposal, which brought the novelty to it. It's really important to go in that direction. Similarly, for nuclei, this was an effect called the EMC effect. You probably have heard about it in talks so far. If not, you will hear about it then. Basically, it's the F2 structure function ratio of a nucleus to a proton. And the fact that it is not straight, flat like this and 1 tells you that the parton distribution function, the quark distribution function, inside the nucleus, inside the proton, is different if it is a free proton or a proton inside the nucleus. And that is what is shown, and that is increases, the impact increases as also you go to higher and higher energies or lower values of X, which is also shown there. A funny anecdote about that, let me tell you. I mentioned to you that we were pitched against each other at Hera. We wanted to do polarized protons, and there was another group wanted to do nuclei. Like Larry McLaren, Raju Venugopalan was not there, but Larry was mainly Mark Strickman et al. And we were given, you get either this or you get that. So what do you do? So McLaren was a good friend of Bjorken. So he wrote to him this letter, which was signed by Bjorken, McLaren, to Bjorken, by McLaren Al Mueller, saying that, hey, this is what we are thinking. We're thinking of putting nuclei in the Hera ring. What do you think about the science? And the response came back, this is a great idea. Love the physics. We'll do it. And I said, will you sign a letter to the director of the lab saying that this is great because Bjorken carried a huge weight. So this is that letter. Unfortunately, I don't have the second page of it, but only the first one that says that this is what we want to do. And so we were sitting on the other side of the fence saying, oh man, Bjorken wrote this wonderful letter. We're going to lose this competition. So Vernon Hughes, who was my postdoc boss at that time, was also a friend of Bjorken. He called him up and said, hey, what do you think about polarized protons in Hera? And Bjorken said, great, we should do that. So will you sign a letter? I said, yes, I will. So he wrote a letter, was completely neutralized. I don't unfortunately have that letter, but I'm told the letter exists. So I'm going to find it eventually in his archives. But these are the kind of things that happen in science as we evolve. And the science was good, as I said, both were good, but we were separated. Fortunately, in the EIC, in the ERIC proposal, we came together. And that really helped beyond this. But this was 1998, I believe, 95, 96. All right. So Daisy had other things in mind other than polarized protons. And so we came from the Europe to the new land, which is now United States. This is where we started working on the ERIC proposal. Peter Paul, I want to mention him here. We are sitting in the room here, which is called the Peter Paul room. This is a seminar room by his name. He was a professor here and also a deputy director for science and technology there. He recognized very early on that this was an opportunity for Rick to move in the direction. So he was very critical in helping us going forward as we went further. I think the XQ squared introduction by Bernd was probably very useful for you, but this is the old plot of how we used to do that using PAW. I don't know how many people remember PAW. You only remember. Now it's all root. But anyway, this is the fixed target XQ squared. This is X and that is Q squared. And you see the ranges. The colliders that were proposed would not have gone out of that XQ squared regime, but would have allowed us to do target fragmentation, etc. But they were all sitting in this area here. The Hera was sitting there, and that is why we thought it was very interesting. And EIC that we're building now will cover some of the fixed target regime, but principally go in the new regime there. It all depends on the energy. If you have high energy, you go in that direction, in that leftward direction going forward. And I saw another modern plot of this same presentation or same plot on modern versions in Bernd's talk, but you see how the distribution of all the DIS facilities as a function of center of mass energy and the luminosity were. And we were here somewhere, we are still here somewhere. All the other opposing or competing experiments have stopped moving forward. Again, the same thing, what G1 spin structure function. And the low X now became a little bit more concrete. We started talking at that time about doing the low X physics. By the way, those names of colored glass condensate or glass, saturation, they all evolved during the same time. So those are, the origins are in this region there. Now, let me switch. So that was the whole origin of it. Let me switch in the more recent past. So this became the first long-range plan discussion in February 2002, the first time the US nuclear physics community was introduced to this concept, and the white paper was written. Any such project which relates to a facility in the United States in the national lab has to get an approval, either depending upon which direction it's going, either the nuclear physics or the high energy physics. Here, RIC is controlled by nuclear physics arm of the Department of Energy, and that's why it went to nuclear physics, what we call NSAC. And this was the first collaboration we found with about 10 institutions and about 20 participants on various kinds. To our great surprise, but also happiness, it was picked up by the long-range plan. That there is a new idea that is coming up, the Electron-Ion Collider. The concept is interesting. It says that what it will do in terms of quarks and gluons, and then it says 2 classes of machine are being designed. Already, there was a competition evolving with Jefferson Lab, and so it didn't exist at that time, really, in the long-range plan presentation. But by the time the conclusions were written, there was a concept. But there was a strong consensus amongst nuclear scientists to pursue R&D. This was important, and it was enough for us because we had done everything on PowerPoint by that time. We needed engineers going forward to make it real, and that meant that R&D was necessary. So for any large project like this is exactly how it should go. The first time you present, if they like the idea, if the community likes the idea, it starts as an initiative. We call it initiative. First formal paper was summarized as annual reviews in 2004-05. 2007, then it followed. A lot of workshops happened here at Brookhaven, at Jefferson Lab. And in 2000 long-range plan, we presented again a lot more sophisticated language. Now we knew GPDs, we knew TMDs, we knew how to do this measurement of the spectator targets, and all that was presented in the high level. And then it says allocation of funds, resources to develop the accelerator and detector technology necessary to lay out the foundation. So first said it was just an interesting idea. This one said, give some money. Now put some money in it. That was five years later. At that time, we started working on various designs of the detector concepts. And what probably weren't, I don't think he showed this, but these were realization of EIC detector. Between 2010 and 4, there was a proposal at Jefferson Lab, which carried the energies associated with their energies, which were slightly smaller than the EIC. Just because the site is smaller, they couldn't have the large colliders, so they had to start with greenfield, which means that if they had to achieve the same competing proposal in science, then they had to develop the magnets on much larger. I told you before that given a magnet, you have a limited dynamic range, which means it limits your energy, which means that if you have a size, and if you have to wait for 50 years for the development of a magnet to get there, then you lose the competition. So you have to go with what you could do in 10 years beyond that point. So they played with that, thinking that, okay, there will be development there, but still the space was not enough to do there. So their design of the detector was associated with of the order of 70 GeV center of mass, not the 100 or 140 that we can do just because we have a large collider going forward. This was the BNL concept. The Argonne National Lab came up with a concept that came from high energy physics, and there was another BNL concept that was here. This, by the way, was developed using the idea that the S-Phoenix detector that exists now and stop taking data will be augmented by forward and backward additional detectors and build upon that to do the EIC science very cheaply. It doesn't work. Technically, now the reality of the S-Phoenix is there, but those are the kind of things that we were developing. Again, this was the science. We went to 2015. At that time, there were two very distinct proposals. This looks very much like what we have at ERIC or EIC, and this was the proposal at Jefferson Lab. And you can see the current CBAF sits here, and in comparison, you had to build this complex, which is a bow tie type CAM complex. It's a bow tie because of the spin manipulation. I don't know if Siberian snakes were mentioned in the accelerator talk today. They were? Yeah. So we have Siberian snakes, 4 of them in the rig complex. They sit somewhere here, there. They have to be opposite in location, et cetera, et cetera. But the beauty of the JLab was that the whole ring is a Siberian snake. So you take a circular ring, you hold one side and flip one side over, and that's what you get, the bow tie. And that becomes a natural Siberian snake. I don't want to go into detail now, but it's very easy to imagine geometrically why it becomes a Siberian snake. But that's what the idea was. I believe it would have worked. It was never tested. We would have liked to build a small machine like that. It's still worth doing it, in my opinion, but it's a beautiful idea, really beautiful idea. But those were the two things that we went in with. And now you start seeing the physics that we developed look like exactly the physics that you see of EIC. The first is, how is the momentum and spin distributed in space and in momentum inside the proton? How do the nuclei interact internally? So this is the nucleus, you hit the proton, the quark inside the proton. What are the color interactions? How do we study this? This is something which could never be done with a fixed target experiment, because most often the nuclear target is a solid state target. That means anything that comes out of the first nucleus gets stopped by the other nucleus. That's another thing that is different about the collider, because it's a gas. That means right next to each nucleus, there's empty space, huge empty space. So if you start creating such jets or such particles coming out, you can actually measure them and not worry about stopping them within the target just because the target is liquid or solid, which is typically the case, not always, but typically the case in fixed target experiments. And then the physics of low X and the nuclei high density. So all of this now has been combined into the science case. I also like to emphasize that you are going into new X and Q square space. It's really important to emphasize that. It's really the key thing, in my opinion, the simplest thing that you can do with QCD is to explore a new region. Because every time we have done that with new variables, we have been surprised. And that's the reason why I keep on emphasizing it. Because calculation in QCD is much more complicated. However much sophistication we get from the theorists, this is really important. Same thing for the nuclei. And that summarizes this whole center of mass energy and your luminosity, the science plot, the internal landscape of the nuclei, the extreme densities, parton density studies. When you start dividing the data based on the spin, you need more data to get the statistical accuracy you get. So you need to get to spin and flavor studies. You need higher luminosity. You need a higher luminosity collider. So that's why you need a higher luminosity here. And then if you want to do the three-dimensional picture, you need to push the luminosity further higher. So this is the reason why the machine developed, as I mentioned to you early on, from ring to Linac ring, where you increase the luminosity, and suddenly you start getting physics reach, which was not even imagined in the early designs. And then when we got sight of this physics, we went back to the accelerated scientists and said, hey, if you can give us 5 times more, we can do more, which is very, very fundamental. And that's how it sort of plays against each other in science. This is a picture from the 2015 long-range plan. We think that we are praying for the positive thing. So the chair of this of the NSAC said this was some felt that the need to invoke powers that higher powers to get the recommendation right. So this is something picture of Donna Giesman. This was a recommendation from the EIC. We recommend a high luminosity, high energy, polarized electron-ion collider as the highest priority for the future facility. After the completion of the then under construction FRIP facility, which is at MSU, the Michigan State University, that was being built at that time. And of course, they had to be careful. They're saying that finish that first and then start the EIC. That construction ended in 2022, and our CD1, CD2 transition happened in 2023-24. Yeah, so this is a very systematically laid out plan in the Nuclear Science Advisory Committee. This then appears in the news that $1 billion collider gets a thumbs up at Brookhaven. That's how really things start moving. Of course, DOE doesn't take everything that comes from NSAC as a recommendation. They have to get an independent renewal and approval. So they went to the National Academy of Sciences, Engineering, and Medicine. That's really routine. And we got evaluated in 2018 about that. And that's the science was compelling. It was fundamental, important things that are really essential and timely. The timely part was also very important. These people who evaluate us are not nuclear scientists. There's a small number of nuclear scientists and particle physicists on it, but there are others from other fields who have to be convinced that the US Department of Energy is going to invest multi-billion dollars. It better be good for the entire public. So it's really important to get that kind of evaluation. The timely part was, in my opinion, very important because previously, they said, oh, your machine is not ready yet. You want this luminosity, the machine is not ready. Is the detector technology ready? And third, is the theory ready? If you get the data, can you interpret it in the way you want it? If you can't do that, then the data means nothing for the knowledge and the investment that we make. So all three had to be aligned. So that timely was not only that the theory was ready to analyze the data, but to get that data, the detector was ready, technology, and the machine had the chance to realize. So that was really critical, in my opinion, going forward. These are the summary of all the papers that came through from 2002, or actually analysis from 1995 to 2021. I think this is something that Bernd showed on in one of his talk presentation. Yes, the detector design that came through the COVID era. And then the site selection happened in 2020. that says Brookhaven National Lab will host this collider in conjunction, in partnership with Jefferson Lab. So now Brookhaven and Jefferson Lab together are building this collider at Brookhaven Lab. You know, this is the design of it. The whole complex exists. This part will be modified slightly, and this is the new electron bunch beam facility. If the physics is the same and there is interest in doing it, it's fundamental, people around the world will come. That's the only place in the world where you have polarized beams, variable center of mass energies, and all nuclei dedicated to the science of QCD. So that's really important. And that's why you see the distribution of institutions from all around the world, a very large number, 900 institutions from 80 countries are collaborating for this project. And you see the high-level map of various things that happen here and the national labs that are involved. So why should we go do this now? I want to finish this with some of these arguments. It's needed for understanding QCD. We talked about the science. Rick reached a scientific maturity when the US had an opportunity to repurpose existing world-class complex. That complex is ready right now. We know how to operate it. We know the people who run it. We know how to carry that further into the next 25 years. It's really important that continuity exists. If people leave after a large project like that goes, then we have a problem starting a new one. It takes longer. These are not things that you can learn in graduate school and go to the collider and turn it on. That's not what happens there. They have built it. They have trained it. They got trained with it. It takes them still a few days to do it. Now they get AI assisted. They might do it faster, but still, that is important. The National Academy said it was timely, and there is a large group of people ready to do it now. I mean, there's a large collaboration now working. You probably are parts of the groups. Your supervisors are now working on it. And this is something that we are looking at you to come in through after these schools, continue your effort towards the EIC and QCD and go forward. So things are really moving. If you go to the ring now, instead of the two rings, you see there are holes there. So the blue ring is being dismantled right now as we speak. This started just last month. This is a magnet coming out and going out of the building. You see that? That's something that is happening now. EIC is really underway. I think a timeline was shown here. The various parts of the detector, the infrastructure, the collider, and the injector complex are being planned and designed. We think that all of them will align around to end of 2024. This is a funding-driven, technically driven timeline. And this is where we start first collisions and start for physics sake, and start around or 8 months to something like that. So that's the approximate timeline. So the way I look at it, 30 years have passed, only 10 more to go for the first collisions. From your perspective, that might be a daunting process. But remember, there's 25 years of physics coming out afterwards, which is going to span a lot of your. I'm not saying that all 25 years you have to do EIC, but we need you in the first few years. That's why we're training and suggesting you. And it's wonderful to be young and enthusiastic and naive. This is the same talk from 2002, and see what I was saying. 3 years of construction of IR and detector, and 2011 first collisions. But it is happening now. You know, costs have changed, the reality has changed, but so has physics. This physics that we could have done without knowing what could be done with transverse momentum distributions or GPDs, without that advance, the last bit of push for luminosity and polarization, that would have been, now looking back, would not have been the full science of EIC that we now can aspire for. And I'm sure that going from now until the 10 years, there are going to be more modifications. So we are going to be running at a different level. Yes, level of things that we think, and we are going to find something new. And after the first collisions that happen in the first collider detector, we will see what we missed. Even if we think that 30 years of detailed thinking has gone into this, we will be surprised by this kind of a program. The gluons will have the ability to surprise us, and nature will. And I think that's something that I want to finish that my talk with, that it will happen in about 10 years, and it will be the only collider that is being built. Something you ever think about, only new collider in the next 20 to 30 years anywhere in the world is the Electron-Ion collider. There is a detailed plan as to what we are trying to do. We have wonderful international partners going forward. And for all early career scientists, this is a place for future QCD. Thank you.